Good morning and welcome to the 2017 AP Chem FRQ 1 walkthrough. It starts with a header text that says carbon tetrachloride CCl4 gas can be synthesized according to the reaction represented above. A chemist runs the reaction at a constant temperature of 120 degrees Celsius in a rigid 25.0 liter container. Chlorine gas Cl2 gas is initially present in the container at a pressure of 0.40 atmospheres. How many moles of Cl2 gas are in the container? Okay, it's asking about moles of a gas. It tells us pressure, it tells us temperature, it tells us volume. It's going to be an ideal gas law equation. So let's go ahead and write that down. PV equals nRT. And we're looking for how many moles we have. So let's just move the RT, divide it to the other side. Gives us N equals PV over RT. If you want to see that a little more algebraically, RT cancels out. So we have our pressure, we have our volume, we have our R, or we'll be able to pick out our R. We have our T, except for one small problem. They gave us our T, our temperature, in Celsius. And we always, whenever we're doing an ideal gas law or any gas law even, Charles Boyle, any of them, need to be in Kelvin. So if we go look at our equation sheet, we find this equation K equals degrees C plus 273. If we go ahead and plug in our 120 into that, we get 120 plus 273, which gives us 393. Now we can plug in and just solve. So go ahead, go to our equation. P is that 0.40 atmospheres. V is the 25.0 liters. R, we have a variety of options, but we're going to use the 0.08206. Why? Because the 0.40 is in atmospheres, and the 0.08206 is also in atmospheres, so that our units will cancel out, times 393. And if we want to check our units really quick, we'll get atmospheres times liters over Kelvin times atmospheres liters per mole Kelvin. That comes from our units cancel, leaving us with just liters. And we will count out our sig figs really quick. 1, 2, 1, 2, 3. Counted as infinite because it's a constant. 1, 2, 3. So we're going to go to 2 sig figs, plug this in our calculator, multiply all the numbers on the top, divide by all the bottom numbers on the bottom, and we are going to get 0.31 mole of Cl2 gas. Easy peasy, lemon squeezy. Once you have that number, you can go ahead and go on over to 2, which asks you how many grams of carbon disulfide, or CS2 gas, are needed to completely react with the Cl2 gas. Okay, we're seeing moles, we're seeing grams, we're seeing moles right here. So that tells us it's going to be a unit conversion problem. So we're going to start with our 0.31 mole of Cl2 gas. And we're looking for CS2. Well, the only thing we have that really ties together Cl2 and CS2 is this reaction right here, which, because it's a chemical reaction, tells us that for every 3 mole of Cl2 we want to react, we need 1 mole CS2. And once we have that, we can go, okay, now we have moles at CS2. Now we need grams. What relates moles and grams? Periodic table tells us our molar mass. Tells us that 1 mole CS2 is how many grams? Well, we have 2 sulfurs. Each sulfur is according to our periodic table, 32.06 grams. The carbon is 12.01 grams. Add those all up, you will get 76.13 grams CS2 gas. Multiply across the top, divide across the bottom, and it gives you 2 sig figs, because 2 sig figs, 7.9 grams CS2 gas. Some things here really quick. Number one, please check your sig figs. I see a lot. I've heard a couple of people like, well, why isn't it 1 sig fig? Because those come from a ratio, they come from a constant, it comes from a balanced reaction. That's actually 1.00000 and 3.00000. They're considered to be infinitely precise, which means if we go across, this has 4 sig figs. These are infinite, infinite, infinite. 2 sig figs is our determining factor. Secondly, points. The 0.31 over here is worth 1 point. Over here, you get 1 point for successfully making this mole ratio. And you get 1 point for your answer, giving you a total of 3 points already earned out of the 10 possible on a long question. On to B. B says at 30 degrees Celsius, the reaction is thermodynamically favorable. Means that it will happen naturally without us putting any energy in or doing any work. That's not the important part. The important part is the next few lines. But no reaction is observed to occur. However, at 120 degrees Celsius, the reaction occurs at observable rate. So pretty much at 20 degrees, it's happening, but it's happening so slowly we can't perceive it. At 120 degrees, the rate is fast enough that we can observe it. Part 1 doesn't even have to do with thermodynamically favorable. It says, explain how the higher temperature affects the collisions between the reactant molecules so the reaction occurs at observable rate at 120 degrees Celsius. And this goes back to KMT. Effectively, what it's asking is, why do faster molecules react more frequently? And that happens for 2 reasons. First, when the molecules collide at higher speeds, they're more likely to stick together. And secondly, by traveling at faster speeds, they have more energy, or can contribute more energy to overcome this activation energy line here. This goes back to the KMT, which talks about the collisions of gas molecules and how do rates work. It's also tied into kinetics. There we go. So perhaps more proper way to say this is a brief kind of explanation, is at higher temperatures, the particles have a greater average kinetic energy than at lower temperatures. Since there is a higher temperature, the collisions have more energy. They have the sufficient energy to overcome the activation energy. You could also talk about how the collisions are happening more frequently. That would be a different explanation. At higher temperatures, the molecules are moving around faster, so they collide more frequently, which means that there is more likelihood the reaction will occur. Either of these refers to both the reaction and appropriate reference to molecular collisions. Either way, plus 1 point. Part 2 says the graph above shows the distribution for the collision energies of reactant molecules at 120 degrees Celsius. Draw a second curve on the graph that shows the distribution of reactant molecules at 30 degrees Celsius. So, 2 things to keep in mind here. First, because it's at a lower temperature, the peak should be up and to the left. Remember, as your temperature goes up, your peaks move down and to the right. As your average energy increases, but the peaks tend to flatten out as there's a wider range of molecules. So, we know for a fact that our peak should be up and to the left. So something like so. And then secondly, we have fewer collisions, fewer reactions going on. Talks about it right here, and it's just a general truth. This curve will flatten out lower. So you should get a curve that looks something like this. This is worth 2 points. The first point is earned for having a peak up here that is up and to the left of the peak here. The second point is earned down here for having a tail that is underneath the original curve for activation energies. Let's talk about this in other terms. At a lower temperature, the average temperature, or the average energy of your collision is going to be less. So this center peak value is going to shift over. Also, because it's a lower temperature, you're going to have smaller variance. The way I prefer to think about this is with like cars on the highway. If the speed limit's 30, you're going to have some people speeding. You're still going to have that people doing 45, but it's far less likely in a 30 mile per hour zone than, let's say, if you're on the highway where the speed limit's 70. Sure, few people are going to be, or majority of your average people are going to be doing 70, but you're far more likely to have someone doing 15 over going 85 because it's a smaller margin or percentage of difference. And you're far more likely to get someone to get over 90, which is the analogy for activation energy here. If it's a 30 mile per hour zone, almost no one's going to be doing 90. In a 70 mile per hour zone, it's possible and actually more likely. And that's the analogy here. All told, at this point, you could have earned up to 6 points. Now on to C. 1C has the archetypical standard draw in the Lewis dot and then talk about the bond angle, or identify the hybridization are the two common questions here. We're going to start by talking about the structure, and then we'll talk about the bond angle. In the box below, complete the Lewis electron dot diagram for the S2Cl2 molecule by drawing in all the electron pairs. First thing you should do when you get any of these problems, draw in the valence electrons. Chlorine is in the 7th row, so it has 7 dots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You'll notice I did this on the opposite side, facing in. I always try to put my lone pairs facing other molecules to make my life easier. You don't strictly need to do this. In fact, it would be technically more accurate to say something like this. But I like to make my life easier. We're going to do it the hard way, and then I'll show you the slightly easier way that will end up being neater. Sulfur has 6. 1, 2, 3, 4, 5, 6. And the same thing again. Remember, you fill in the 2 dots on the top, then 1 dot around each of the sides before doubling up. This is due to Hund's rule, which states that electrons will fill up unfilled orbitals one at a time first, then start doubling up. Once you've drawn in your dots or your electrons, pair any unpaired electrons together to create a single molecule. So like chlorine only has 1 unpaired dot, so it's got to connect here. This chlorine only has 1 paired dot, so it could go here, but then this sulfur wouldn't be connected. So I'm going to connect it to the sulfur next to it, which leaves me 1 unpaired dot like so. And this is an accurate drawing. However, I'm a neat freak. So I'm going to rewrite this slightly differently. And then draw in my bonds, then go back and add in my lone pairs. So this chlorine is connected to the sulfur, this sulfur is connected to the sulfur, this sulfur is connected to the chlorine, and then I draw in my lone pairs, which will give you a slightly more accurate representation of the molecule. Now, either one of these will work. Take your pick, but that is your correct electron configuration drawing. Question 2 asks, what is the approximate value of the CL-S bond angle you drew in part C1? If the two bond angles are not equal, include both angles. Whenever you have this question, what you need to ask is, what's your steric number? As in, how many things or regions of electron density is your molecule talking about? You're talking about the CL-S bond, so you're talking about CL-S, you're focusing on this S in the middle. Or this S, we'll talk about both. If I look at this S first, I go, okay, it's got a lone pair, another lone pair, and 2 bonds. It's connected to 4 different things. It has 4 different regions of electron density. Its steric number is 4. If I look at the other sulfur, which the problem does tell you to do because it says, okay, if they're not equal, I notice I have the same pattern. So because the steric number is the same, their approximate bond angles is the same. I'm going to go ahead and tell you right now, if they have this little thing in parentheses, My immediate read on that as a person who takes lots of tests is that's not actually what's going on here. They're just covering their butts. So that way, if someone gets the wrong answer, they don't tip them off that the right answer isn't the one I got. It's a way for them to cover themselves. But the fact they felt the need to add that is suspicious. I'd still double check if I got different answers or the same answer. But I'd be willing to gamble that they didn't actually have different things. Regardless, gambling or not, you look at it and go, okay, they both have a steric number of 4. At which point you need to think back to this chart, this table that you should have memorized. Based on the steric number of the molecule, which is the number of the number of regions of electron density it has, will determine the approximate bond. Numbers will vary exactly based on exact structure. For instance, these lone pairs will repel more than these bonds, so the angles will be slightly off for those. But in general, it gives you a good number. Okay, and then you go down, okay, well, if your steric number is 2, your bond angle is 180, 3, 120, 4, 109.5, 5, 90, or 120, depending, 6, 90. In this case, our steric number is 4 for both of them, so our answer is this 109.5 for a single point. And this drawing, by the way, was worth a single point. As a quick review, let's talk about bond angles. If you have a steric number of 2, you have a straight line, something that looks like so. Remember, double bonds count as one region of density because they're one factor for your steric numbers. If you have a steric number of 3, you get this kind of triangle, 120. 4 is where you start having to branch into 3D. These are both two-dimensional figures, but once you get to 4, you have this 3D trying to space out those electrons as much as possible. And that's the only one that's weird, 109.5. Thankfully, which makes it really easy to memorize. 5 is a pain in the butt because it could be 90 or 120 depending on the molecule. Here, the Cl is at a 90-degree angle from each other, but if you're going around this kind of circle here, it's at 120. Please keep in mind that the drawing of where these are depends more on the lone pairs, but that is typically beyond the scope of the AP exam, so I wouldn't expect to see this, but it's still useful information to know. 6 is always 90 degrees because it's effectively like a cube. On to D. D has a lot of superfluous information, but let's go through it really quick. CCl4 gas can also be produced by reacting CHCl3 gas with Cl2 gas at 400 degrees Celsius, as represented by the equation here. CHCl3 gas plus Cl2 gas gives us CCl4 gas plus HCl gas. At the completion of the reaction, the chemist successfully separates the CCl4 gas from the HCl by cooling the mixture down to 70 degrees, at which point the temperature of the CCl4 condenses, aka turns into a liquid, while the HCl remains in the gaseous state. Okay, that's very important. Don't forget it. We'll come back to it. Identify all types of IMFs present in HCl. Okay, these two questions will be on every AP exam, so star them, don't forget it. Let's put the little star here because they're important. First, it says identify all types of IMFs present in HCl, which means you should probably draw it out. In fact, I encourage you, whenever it asks for identifying all types of IMFs, draw it out. So we have H with a single dot and Cl with a single dot. Again, I'm just going to have them face each other, make my life easier. So I can just connect the dot here, like so. And there you go. HCl looks like that. Now, hydrogen is a nonmetal. Chlorine is a nonmetal, which tells us right off the bat that this will not be an ionic reaction. Okay, chlorine is farther to the right, and thus will be more electronegative. So you're going to have a positive side and a negative side. Partial negative, partial positive. So let's go through the list then. Is it ion-ion? No, because it's not between a metal and a non-metal. There are no ions present. There are no ions present. So ion-ion, ion-dipole right off the bat. Takes us to dipole-dipole. Is there an unbalanced? Is there a polar molecule? Yes. Chlorine is more electronegative. It's going to pull the electrons closer to it from this bond, giving you a negative side and a positive side. So we have dipole-dipole. Hydrogen bonding. I put a little star next to it, not because it's important, it is, but because hydrogen bonding only happens in 3 specific circumstances. Those circumstances are HF, which some textbooks won't agree with, but generally the AP exam does, HO, and HN bonds. If you do not have one of these 3 bonds, you do not have hydrogen bonding. Even though we have hydrogen bonded to something and it's a very polar bond, this is not hydrogen bonding. Secondly, it is, strictly speaking, hydrogen bonding is a subset of dipole-dipole. And because that is a very gray area, you typically won't see things about it on the AP exam. That's not to say it won't happen, just probably won't show up. Finally, is there dispersion forces? The answer is always yes. If you have electrons, you have dispersion forces. Always, always, always. So, what IMFs are present in HCl liquid? Dipole-dipole, disperse. Part 2 says, what can be inferred about the relative strengths of the IMFs of CCl liquid and HCl liquid? Justify your answer in terms of the info above. Please be very careful here. It doesn't ask what are the IMFs or to justify it. This is actually a simpler problem than what we've seen in the 2018-2019 tests. In this case, it's asking you to compare the strengths. And the only thing we know about strengths, or the only concrete thing we know about strengths, is the boiling point. At what point do they boil? Now, they made it tricky on you because they didn't tell you when it boils, they told you when it condenses. But that's the same idea. At 70 degrees Celsius, CCl4 condenses, but HCl is still a gas, which tells you that CCl4 has a higher boiling point. How do I get there? Well, let's put it this way. If I were to go from 0 to 70, at some point in between the 0 degrees Kelvin and the 70 degrees Celsius, which is actually 343 Kelvin, at some point in there, the HCl turns into a gas, but the CCl4 doesn't turn into a gas until 70 degrees Celsius. That's when it boils. That's when it turns into a gas. That's when it makes that transition. Because it says it condenses at 70, that's also the point at which it boils, which is higher than HCl because it's still a gas. It's a little tricky. Be careful with it. But because CCl4 is a liquid, HCl is a gas, it tells you that CCl4 has stronger IMFs because it has a higher boiling point. Or it condenses first, which means it's more attracted to the other molecules around it. Either way, you have to explain it in a fully logical sentence. So something like that might be, the intermolecular forces among CCl4 molecules must be stronger than those among HCl molecules because the CCl4 condenses at a higher temperature than HCl. There it is. Each of these are worth 1 point each, taking our total for question 1, which is a long question, to 10 points. And all your long questions will be 10 points. The nice thing about the 2017 exam we're going to talk about for a second is that it tells you that the long questions should take about 23 minutes. The short questions should take about 9. If we look at what we're going to get on the exam that they're giving us this year, they told us it'll be 25 minutes with a 5-minute upload time, which is slightly longer, about 2 minutes longer than the expected time for internet kerfluffles and issues than is typically expected. And they're, instead of a 9-minute problem for the long answers, they're telling us 15, which is a notable step up, about 1.5 times. But there's also because the short questions have gotten a little harder since 2017, but not by much. With that said, this is about the length you should expect. Manage your time carefully. Thank you. Have a good day.